So this will be day 2 for probability rules. We're going to hit some basic stuff, and we're going to go ahead and get a few more definitions. It's pretty important, so really stay with it and get all the little rules down, and that's going to be basis for more complicated rules. So everything builds on itself. Please don't fall behind. So just for starters, again, probability of an outcome. This is just a number value that represents the likelihood of the occurrence of an outcome. I need that as a fraction or as a decimal to 4 places. That's our rounding requirement. Also, we could call it the proportion of time the outcome would occur in a very long series of repetitions. This is based on the law of large numbers. Now, we may have inferred or hinted to the law of large numbers without maybe just formally defining it, but we actually worked on it on our half day on Friday with the activity of rolling the pigs, because with the outcomes that were present, I believe there were 6 of them, that they have pretty much defined probability after having rolled those things indefinitely. We didn't, but they have been rolled indefinitely. The pattern of outcomes falls into view. It just falls out for us to see. So we have already worked with the law of large numbers. So formally, it's just saying that the long run relative frequency, remember relative frequency is proportion or percent, so that the long run relative frequency of repeated independent events gets closer and closer to a single value. And we call that single value the probability of the event. All right, this is obtaining probability values through observation rather than just using mathematical formulas and things like that. So that'll have a specific name. So because this definition is based on repeatedly observing the event's outcome, this definition of the probability is often called empirical. Empirical is another way of saying scientific, and you know that the scientific method uses observation. So we're just conducting the experiment, observing the outcomes, repeating many times until the true expected outcome falls out for us to know. And remember, long run is indefinitely long, infinitely long. Okay, law of averages. You might have just said to yourself, you know, I have just had the worst week ever. You know, Sunday was bad, Monday was worse, Tuesday wasn't great. Here it is, Saturday. I think tomorrow's going to be a good day just by the law of averages. Like, there is a good day out there. And if you experience enough bad days, then it will be a certainty that you'll see a good one. That's the law of averages. Your law of large number doesn't say anything about short-term behavior. In fact, it leaves it open that short-term outcomes are unpredictable. All right, so relative frequencies even out only in the long run. And this long run is really long, infinitely. I've said that. So this so-called law of averages, that an outcome of a random event that hasn't occurred in many trials is due to occur, that's not true. So if you have a big family and you have a lot of kids and your first 6 kids are all boys, that does not guarantee that your 7th child is going to be a girl. The 7th child is just going to be a half chance of getting a girl, half chance of getting a boy, just like the 1st through the 7th were, or 6th. So yeah, things will fall out in the long run. You would expect to start seeing this happening or this not happening, but you know, just because you have a certain run of a single event happening or a single outcome doesn't mean that some other outcome must happen in the next one. All right, so theoretical probability. These are probability values arrived at through calculations, formulas, things like that. Empirical probability these are going to be probability values arrived at through observation or simulation. So where we're going today mainly is the theoretical probability. We're not just going to roll die just to see what happens. We're just going to get some mathematical certainties that will help us calculate probabilities. All right, so here's the one you probably already know. So A is an event. So the probability of event A is the number of elements in A that come up as A over the total number of elements in S, which remember is your sample space. So it's successes out of total. That's what probability is. I'm assuming you already know that, but here it is formalized. So we have two requirements for a probability value. Probability value is a number between 0 and 1 inclusive. Doesn't say inclusive, but you could have a 0 probability or a certain probability, which would be 1. So the probability of any event A is that it will be between and including 0 to 1. So you cannot have negative probabilities. You cannot have a probability of 1.8 or 2.0. That can't happen. It's either a 1, which is certain to happen, or something down to 0. Okay, probability assignment rule is just telling you that the probability of the set of all possible outcomes of a trial must be 1. All right, so if you know 6 of 7 outcomes, if you know those probabilities, you can add them up and subtract them from 1 to get the 7th, because they all must add up to 1. So the probability of your sample space, remember sample space represents the set of all possible outcomes, must be 1. And this square, or rectangle if you want, is a Venn diagram. We use Venn diagrams quite often. They help you to visualize things. And this is your sample space. One rectangle with nothing in it would represent all possible outcomes, especially if it's labeled S. All right, complement. All right, you often hear they make a good couple because the one complements the other. That doesn't mean that they share a lot in common. It just means that whatever she is good at, he isn't. So he benefits from that. And whatever he is good at, she isn't. And she benefits from being with him. So that's what a complement is. That's not necessarily the same thing. It's really more like the opposite thing. So the set of all of outcomes that are not in the event A is called the complement of A. And it's got its own notation with the superscript C. All right, so A or not A. The probability of an event occurring is 1 minus the probability of the event that doesn't occur, because there are only two outcomes. Either that event happens or it doesn't. So the probability of A is 1 minus the probability of its complement. So this circle represents all possible outcomes that we can assign to event A. Maybe event A is that the creature is a dog. All right, and so those are where A is occurring. A complement is any animal that's not a dog. So you're either a dog or you're some other kind of animal. There are no other choices. All right, so the whole sample space has to add up to 1, and these two are two parts of the sum that equal 1. So if A complement plus A equals 1, then you can algebraically convert to this. All right, so here's what I just said. The complement rule states that the probability of event A plus the probability that A doesn't happen equals 1, because there are no other options. The sample space is 1 because the sample space represents all possible outcomes. Therefore, the sum of the two are 1. That's your entire sample space. And that's because A happens or it doesn't happen. There are no other choices. Now, this is a really important rule, the at least one rule. So the probability of at least 1 equals 1 minus the probability of none. Or the probability that at least one outcome happens is 1 minus the probability that none of those outcomes happen. Now, this is a great way to calculate probabilities when things get complicated, because the probability of at least one could be an incredibly hard computation. And you would need to know all of the possible outcomes that are, that are beyond none, okay, which could be many. But the probability of none is probably one thing of your sample space, not many things. So 1 minus that would be your probability of at least one. You'll see examples of this. All right, probability of A equals 0 only if A is certain not to occur. That's an impossible event. So the probability that next month is May is 0 because next month is November. It's not going to be May. All right, the probability of A equals 1 if and only if A is certain to occur. So again, the probability that next month is November is 1 because that's what next month is going to be. There are no other options. Okay, now we come to where we may have more than one event, and we have to know how to calculate probabilities when those things interact. So the addition rule for disjoint events. These are events that have no outcomes in common. Thus, they cannot occur together. These are called disjoint or mutually exclusive. Right? These are exactly two things that just can't happen at the same time. Tomorrow can't be Saturday and Sunday at the same time. Right? So those are mutually exclusive or disjoint. Okay, independent and disjoint are not the same. We'll talk about that later, but don't mix that up. Independent and disjoint, independent and mutually exclusive get confused as being the same thing. They're not. All right. When we have disjoint events, we use the word or. That means addition in the language of probability. Actually, we can use or for non-disjoint events too. Let's just go ahead and say or means addition in the language of probability. Remember, and means multiply, or means plus. All right, so note that A or B, probability of A or B, can also be written with your probability symbols or your set symbols. All right, this is a symbol that looks like a U, so it's really easy to remember this symbol as union, and union is another way to say or. So if you see this, you can say probability of A union B. You can say the probability of A or B. So you have a rule for how to calculate disjoint events when you want the probability of A or B. So for two disjoint events, A and B, the probability that one or the other occurs is the sum of the probabilities of the two events. So the probability of A union B, probability of A or B, equals the probability of A plus the probability of A. And that's provided that A and B cannot happen at the same time, that they are disjoint or mutually exclusive. That is your formula, addition rule for disjoint events. So here we go. Probability of married or divorced. All right. We're going to go ahead and assume that those things can't happen at the same time. Let's not argue the point. That would be the probability, oh, I'm sorry, I didn't see the never. Probability of never married or divorced. All right. These can't happen at the same time because the only way you could be divorced is if you were married at some point. So never married or divorced is the probability of never married, that's 0.353, plus the probability of divorced, 0.071, and so that's 0.424. Easy stuff. Okay, we have multiplication rule for independent events. Remember, independent means that these are things that cannot happen, well, let me get this straight. When two events are independent, knowing that one thing happens doesn't tell you that the next thing will or won't happen. You don't have any information to infer what's going to happen next. So remember, the word and means multiplication. We've already run into that with your fundamental counting principle. So it means multiplication in the language of probability. And note that the probability of A and B can also be written as the probability of A with that U symbol kind of flipped upside down, that is the symbol for intersect, or the word A. So probability of A intersect B. That's the same as probability of A and B. You just got to get used to the symbols. It's easy because union looks like a U. The other one is not union. All right, so the multiplication rule for independent events. For two independent events, A and B, the probability that both A and B occur is the product of the probabilities of the two events. So, probability of A intersect B, you can also say a probability of A and B, is the probability of A times the probability of B, provided that A and B are independent. Okay, so knowing that A happens doesn't tell you anything about whether or not B is going to happen. All right, in a Venn diagram, remember the disjoint events showed the circles within for the two events being separate? All right, in this particular case, the two circles overlap. So you have this kind of pumpkin colored circle is the probability of B. This bluish circle is the probability of A, and where the two overlap is where they can both occur at the same time. So this is A and not B. This is A and B. This is A and not B. Or B, did I say that wrong? This is B and not A. This is A and B. This is A and not B. So these are not disjoint. There is an intersection here. All right, so two independent events, A and B, are not disjoint, provided that the two events have probabilities greater than 0. Okay, I'm going to pause because I need to set up for this. But one thing that I might do is go all the way back to an earlier slide, if I can get there, to here. Remember that I said note for disjoint or mutually exclusive that those two words do not mean independent. Remember what independence means. It tells you that if A happens, that you really don't have a clue what B is going to do as a result of A happening, right? Now these two are disjoint, right? That means that A and B cannot happen at the same time. Okay, I'm just going to look at you and say to you, A happened. What can you tell me about B in this particular case? Well, if you look close, if you know that A happened, you should be able to tell me that B didn't, right? Because they can't happen at the same time. That is knowledge of what B is going to do, knowing that A happened. So when things are disjoint, they are by definition not independent. Because when one happens, you automatically know something about the other. It doesn't happen, right? So disjoint is not the same as independent, right? In fact, when things are disjoint, by rule, they are not independent. So I'm going to pause for a moment and set up for that last slide. So stand by while I do that. All right, sorry about the little pause there. So we're going to look at a table, a two-way table, which is really, really important for, well, a whole lot of things in statistics, but especially it has a lot of applications in probability. This notion of independent versus dependent events. So we're looking at the interaction between education and the age of a person, and it's some big survey with what, 166,000 plus individuals. So there's your total. Remember, these are your marginal totals here and here, and each and every one of the other cells represents a joint probability, an and. So this would be this number here. Let me go ahead and circle it. That would represent that age of people and this education level. So it would be 35 to 54 and 1 to 3 years of college, just for example. And they're all like that. Okay? So let's go ahead and call event A that will be a person is 55 or older. All right, so that is event A. And we'll just go ahead and call event B and that will be that a person has 4 or more years of college. All right, it's always good to do this to define your events so that you understand what you're doing and others know what you're doing. Now we can calculate probabilities of these things. So let's say we want the probability of A, all right? Person is 55 or older, all right? So there's the count of those people who are 55 or older. That's out of the total. So that'll be 52,022 divided by 166,438. And I will spare you the delay in getting the calculators out. That's 0.2297. Okay? And then we can do the probability of event B, that a person has 4 or plus years of college. And that would be the total for those people, again, out of the grand total. So that would be 38,225 over that same 166,438. And that would give you a probability of, whoops, I have my numbers wrong. Let's fix that. And that would be 0.3126. My bad. So 0.3126. I got a lot of things I'm juggling here. This is your 0.2297. Okay? All right. So let's go ahead and look at the probability of A and B. Okay? So if these things were independent, we would just go ahead and say the probability of A and B. All right? That would equal the probability of A times the probability of B when A and B are independent. And we're not told that they're independent, so that would be a big assumption here. But let's just go ahead and assume that they are. That would be 0.3126 times 0.2297, and that would give you 0.0718. All right? We can actually get this directly off the table, though. So we can just compare to the table. Because we have the intersection of a person being 55 or older and having 4+ years of college. That would be, since I left things on there, let's go ahead and pick red. That would be this over this, right? So in that particular case, we could just say this up here, that the probability, and I will write this out in words, of 55 plus or older and 4+ years of college Okay, I don't know why you just went haywire on me. All right, that would be 8,005 over 166,438. If they're independent, it should equal this, but guess what? It actually equals 0.0481, which is different. All right, so clearly being, age and years of education, those two things have to be dependent on each other. And we can actually look back at this table and maybe figure out what that dependency is. So if you look at the older people, do you see how their increasing college level drops off? Like you start with the not high school grad and go all the way up to 4+ years of college, and the number is dropping. Whereas the younger people, that number is starting out small and getting bigger. So can't you kind of say that the older you are, the less educated people tend to be? And if you can see that, that is a dependency. All right. So let's just call this closer inspection. And that's just working right off the table. And that reveals the older the person, the less educated they may tend to be. All right, if these two events are independent, we should not be able to see that. All right, since we are seeing it, they're dependent. You see it in this number as compared to this number, and that's the way you can tell if events are independent or not. Interesting. Okay, so let's close this down and go back and close out the presentation. So we worked on this. All right, so your AP tip. So for even the most simple probability problem, please show work, right? Please show your work. It may even just be to show the fraction that you use to calculate the percent. If you don't show work, AP people are told to count those things wrong, okay? So please follow that piece of advice.